Okay. In the morning, we explained the piezoelectricity and the ferroelectricities. And the piezoelectricity is just a relationship between the force and the polarization, or it's a combine of the deformation and the polarization. We have two ways to describe it. We can call it piezoelectricities. You apply a stress, you can change the polarization. So the piezoelectric coefficient can be defined as the Coulomb pollutant, or we can define the converse piezoelectricities. We apply an electric field towards the deformation, and the unit can be defined as the meter per volts. These two, they are actually the same, and we use tensor to describe it. And one important component is the D33, which represents we apply the force at z direction perpendicular to the z directions area, and we get the polarization at the z direction. Or we apply electric field at z direction, we cause the deformation at z direction. That's the D33. And the piezoelectricity depends on the symmetry. So if the crystal does not have inversion center, then it is piezoelectric active. And if this material has the intrinsic ferroelectricity, the P does not equal to 0, then the Nondal theory has approved this kind of properties. It will have two stable polarizations, and this is the ferroelectricities. If this polarization can be switched by external field, we call it ferroelectricities. Means it is intrinsically charged or intrinsically polarized. And so the ferroelectricities, the polarization can be changed use external field. And so it has this hysteresis loops. And the hysteresis loops has 4 important points. It has 2 coercivity. It has 2 intrinsic polarization. And these loops should be symmetric, and it should be counterclockwise. That's the ferroelectricities. So if we want to study the ferroelectricities at a nanometer scale, we will use the piezo response force microscope. And this PFM is based on the piezo response, the piezoelectricity. So we place the samples on top of our stage, and we can apply an electric field on our sample. So we can actually apply tip bias or apply a sample bias to reduce the noise, to reduce the disturbance from the environment. We use the modulation, or we use the telephone theory. We get it modulated with AC field. So we apply voltage actually at a certain frequency, and then our deflection will be proportional to D33 and this frequency terms. And then we can get the amplitude directly get the D33, and the phase can be 0 or pi. That's our theory, right? So if we take a look at our we take a look at these structures, we can use this one as a demonstration to show our the PFMs. The PFM has a first or has a most important one is we apply the voltage, we apply the field in the z direction, and we study the deformation at the Z direction. That's the D33. So this D33, this piezo response, the amplitude is proportional to D33. But in our actual crystals, it can have various polarizations directions. For example, like this one. And since we only studied the D33, the D33 has a confined direction. It's just Z direction field, Z direction deformation. So even our domains, it has different directions, but we only study its Z components. We don't study its full it's the totally the polarization. We only study its Z components. So for those kind of domains, we only get the Z components. So the amplitude can be changed due to the direction of the polarization. And then about the phase, because we only study the Z direction, we only study the Z components. So it has only two directions. One, follow our electric field, or opposite to our electric field. So the phase has only two values, 0 or pi, and the amplitude can be changed due to the orientation of our polarizations. So that's the PFMs. So usually one signature of PFM is that our amplitude is always positive, and the phase is always 0 or pi. It cannot be other values. That's the PFMs. So, and for example, for this one, it can be this paper, they study the section of this sample, and on top layer is facing up, bottom layer is facing down. So cross this section, we can tell the amplitude is changing, but the phase is only two values. So that's the PFMs. So since our polarization is in the space, it has in principle it has three components, X1 and Z. So this vertical PFM only study the Z directions components, but it still has another directions, that's X and Y. Okay, so let's use the probes. Let's use the AFM cantilevers to take a look. So here is my AFM probes. So then I place my my crystals on the structures. I place my crystals beneath the probes. So I make my directions following the right-hand coordinate. As this one is X, this one is Y, and this direction is Z. Okay, the Z is perpendicular to the board. Okay, so once we have defined orientations, so we apply heat bias or sample bias. Our electric field is on the Z directions, so we apply the E is on Z. So we only study the D3. And the vertical and the horizontal are the two values we can get studied. So let's consider we shine the laser on these probes, and then the laser will be reflected by the probes. So I draw a green line here. So the laser is shown here. and the reflected laser in here. That's my detector. And the detector, if the laser is moving up and down in this direction, this is vertical. And if the probe itself is rotated or tweaked in this direction, our laser will be moved along here. So the horizontal just means we cause the probe to move. We detect the torsion movement of our probes. So the vertical value represents the deflection. Our probe is bent in this way. And the horizontal value, it means the probe is kind of this rotation. So I call it torsion. Okay, so so we can consider. So actually, the deflection or the vertical actually means we apply a force on the z direction, right? The probe just sends a force in this z directions. And what about the horizontal? Horizontal just means we apply a force in the x direction, right? If we give a force on the x directions, our probe will be torsioned or will be rotated in this way. How about we apply a force in the y directions? It will cause the probe to be something like this, right? So that's the three movement in the x, y, and z. So the vertical is detecting the z, and the horizontal detecting x. But the y movement is just something like this. In principle, the y direction movement, it will cause the probe slightly vertical, slightly movement in this direction. So usually we would place it here, a slightly y movement. But this term is so weak. So usually we don't consider this one. We don't consider this one. So mainly we consider the vertical is deflection, the horizontal is the torsion. In our coordinate here, the deflection or the vertical represents the z direction force, and the horizontal in our coordinate here is the x directions. So if we have a polarization, and this polarization, we place it in the space, it will have the px, py, and pz. And then we place it in this fashion, and from the vertical, we get the deflection. And we get the D33 times the voltage, the VTB or VSB, sample bias or T bias. And then, of course, there will be a sine omega t, okay? And then the horizontal, it will be the torsion, which will be also the third, also will be the D3 because it's the Z directions electric field. And so it will be VTB or V sample bias times sine omega t. The only thing left is here. The only thing left here. So because our material is kind of, sorry, need to go back to the quite beginning. Because we want to do a materials in this our probes should be torsioned in this x directions. So we consider the deformation or we consider the stress. We should consider these terms. Those tau terms, we just call it, we just wiggle the crystals, or in Chinese we call it 剪切, right? It's not expansion in the x or y directions. It's this kind of wig movement. So in the textbooks, in the theory of the in the theory of our piezo response, we think the x and the y movement detected by AFF is 34 and 35. It's not 31 and 32. 1 and 2 represents expansion in x direction or expansion in y directions. So it's a kind of weak mode. So we use 4 and 5 here. So usually in here, we would give it 5. 5 is for x, 4 is for y. Okay, so here is the horizontal. So this 33 represents the PZ, and the 35 represent the PX. How about PY? Because we have the PZ, PX, PY, we have all the 3 components, we can get back P. So the thing we will do is we rotate our sample. If we rotate our sample by 90 degrees, if we rotate the sample by 90 degrees, the samples will be, here is the X, Y, and Z, right? So at these directions, it's the same. We apply the bias, we apply the voltage, or we apply the electric field in the Z directions. We apply tip bias or sample bias. So that's the EZ. Okay, under this, we will get the vertical. Again, it does not change. It's still the deflection. It's the D33 times VTB or V sample bias sine omega t. But in this setup, since we rotated the sample, the x direction is parallel to the probe. It can only cause the probe to be something like this. The py will make the probe to do torsional. So the horizontal will be torsion, will be D34 VTB or VSB sine omega t. So here again, it gives us PZ and PY. So to do 2 images, we can get PZ, PX, PY. And with that, we can reconstruct it back the polarization. So this kind of this kind of experiment, we call it vector PFM, to get all the 3 components back and to make together a frame. And of course, this kind of frame is just made up using softwares. And the experiments here is not easy to do because under PFM, we need to rotate the sample. And we must make sure we get we get the same frame back here. So in experiment, it's not that easy, but it's kind of useful. So in around 2000 years, just before the 2010s, we're still studying this kind of things because the crystals is still useful for us. But after that, this field is reducing because almost all the work is done. But nowadays, the 2D materials is back, and we found that the 2D materials is also ferroelectric. So this work is come back again, becomes popular. So hopefully they can still get back this kind of vector PFM. But in practice, in real experiments, this one to get this done is relative difficult or relative time consuming. Okay, so the K here is if we want to get this done, we need to rotate sample. Okay, not like the some paper said or some textbook said we should change the scan directions. No, you change the scan directions, you does not change the properties of our AFM detectors. You scan in this way. The horizontal represents the X. You scan in this way. The horizontal still represents X. It does not change. It does not change. So if you need to get this done, rotate sample. Rotate the sample. And actually, we always recommend you to scan at this fashion. We scan at this fashion. And we scan this fashion because if you scan in this fashion, your friction between tip and the sample will be this way. So no friction signals will go into your horizontal. If you scan in this fashion, and then the friction will cause the probe to be torsional. And then the friction signal will go to the horizontal. So your torsional displacement will be mingled with friction. And we don't want to do that. So please scan in this direction, in this fashion, okay? In Brooks setup, the icon and the multi-mode, we define this fashion, scan direction parallel to the cantilevers. The Brooks call it 0 degree. The Brooks call it 0 degree, right? But in other AFM setups, you may using Oxford, you may using Hitachi or something. There are many other AFMs. You can also use the same theory. It's the PFM theory is always the same, but they may change different definitions. So don't remember, we always use 0 degree scan. No, we make sure the scan is parallel to the cantilevers. That's good enough. Okay, so in other AFMs, you can change it accordingly. But in Brooker, it's 0 degree. Okay. And the second thing we would also discuss, is about our field. So here is clear, right? So for the terms of the coefficient, the piezo coefficient. We have the D33, D34, and the D35 here. And some users, they are interested in another component. For example, some researchers, they would like to use D15. D15 is famous, or D15 is important because this D15 is an important component inside the PZT. This PZT's crystal structures, they have a significant D15. And so some researchers, they want to use D15. So this D15 means we apply the electric field at X direction, and then to detect the torsional or the wiggle at X direction. So it means we apply a X directions electric field, and we cause the crystal to be wiggling at these directions. So this one is also important. This one is also important. So if you want to apply this kind of voltage, or if you want to apply this kind of electric field, I'm sorry, we may need to do it by ourselves. So we can still do the AFMs. We can still do the PFMs. That's our probes. That's our crystals, or that's our structures. So we want to detect X directions. Now the X direction is this way. So we call this is X directions, okay? Perpendicular to my board. Okay, so I need to apply the bias, or I need to apply the field in this way. So usually you can use external source to do this. It's okay, you can use external source to do this. But if you still want to use AFM setup, we can do that in this way. Let me draw in this way so it will be easier. So here is my probe. So here's my probe. So here's my probe. So the y directions. So the y directions is perpendicular to the board. Okay. And then x directions is here. Okay. How? Okay. How? Then we put the probe. The probe does not need to be conductive because we don't want to apply any tip bias here. So the probe is non-conductive. Okay, and then the bottom of our crystal is also non-conductive. We paste this side. We paste this side to our sample bias. And this side to grounding. And then you can apply sample bias here, and then you actually apply an electric field in the EX directions. That's a way to apply this electric field. Since your probe is non-conductive, so you don't worry there will be some Z components. No, because the probe is non-conductive, so it's only this way. So the electric field is only this way. So you only this way, you still detect the torsional wiggling of the of the probe. So you detect the horizontal, which will be D15. Okay, right? That's the way to do it. Of course, it's the same fashion. You can use the vertical to get the D13. Yeah, it's the same, right? But in the real setup, for the PZT, the D1 file is important. The other things, no. So you can do this kind of setups based on your own crystal structures you can choose. But I have to say, nowadays we are focusing on 2D materials. The only this three is important. The others not important anymore. Okay, so we keep going. So the probe selection, if we want to apply, if we want to apply the Z directions, if we want to apply Z direction electric field, our probe has to be conductive. As this way, we can establish a Z direction electric field. So the probe has to be conductive, and we usually coated the probe with some metals. So the most common choice is this SMPIT. This probe is coated with palladium. Palladium, yes, and it's a quite good conductor. But this probe, I have to say, is not robust because the palladiums, because it's platinums is not affinitive to the silicon. So this one is easily to be damaged. So this probe is not that robust. And the second best, another choice is to use the MESP. This MESP is based on cobalt, and the cobalt is good. Cobalt can attach to the silicon stronger. So MESP is also another choice. But for this kind of PFMs, we need to consider two things. The first is about the sensitivity. So this is our crystal. And we have a probe. And then we apply an electric field. And then this sample is expanded due to the piezo effect. So the sample expanded. And the expanded probe, the expanded, they will change in the height. This change in the height, I will use the delta H. The delta H is defined by D33 and the VZ, right? Oh, sorry, VTB or VSB. So this delta H is defined, is a fixed value, just determined by your parameters and the D33 itself. And then how we detect this delta H? We actually have a probe. So here. So we use the photo detector to detect the deflection of the probe. So only the angle of my cantilever changed, it can show a deflection, right? You consider this way. This is your probe, this is your laser. And I'm sorry, this is your detector, this is the laser. So if the probe is moving up and down, the cantilever does not make any deflections. The vertical value will not change, right? Because the whole thing is moving up and down, up and down. So the moving up and down does not change the vertical values. Only the probe has some deflections. It changed the light path. So we actually detect the deflection it just means the angle change. Okay, so let's consider this way. So this is my this is the sample, and this is the sample, and it changed delta H. And here is a short probe. And then I have another way. This is a sample. This is the delta H. And I have a quite long probe. Sorry. I have a quite long probe. So this angle change, this angle change should be just delta H divided by the length is nearly the tangent theta or nearly the theta. So the length is longer, the theta change is small. Because the delta H is the same, because the sample's deformation is the same, it's defined by D33. So the longer the length, the small change of the angles. The small change of the angles means the vertical value changes smaller. So if we want our vertical to change dramatically, we want our length to be short. So the AFM demands, so this PFM demands a short probe. So we would recommend these two. The MESP RC and the DDESP. The MESP RC, the length of the MESP RC is about 125, and the nominal under the nominal length of the SMPIT and MESP is about 220. So we recommend this MESP RC. This probe is short. It's good for the PFM. And then the next demand of the PFM is the stiffness. It's about the K, and we will go that in the afternoon. That's a key point here. Okay, so hope I explained it. Okay, it's why we need to choose the short cantilevers. And then we will have then the next thing we need to, let me see, where is the face, the round, the hysteresis? No, let me think, where is the statistic charge? Oh no, I think I missed one page. Okay, I'll just explain here. Okay, then the next topic is about the probe selection. It's about the spring constant. Once we want to talk about the spring constant, we want to talk about the first enemy of the AFM. I'm sorry, of the PFM. That's the electrostatic charges. So we get some review about yesterday's problems. Yesterday, we talked about KPFM. And what's the KPFM? It's the probe. It's the sample. We apply certain sample values or tip values on the probes sine omega t, right? And this omega has nothing to do with the, and this omega could be anything, but for usually setup, we choose this omega to be omega 0, okay? After we apply these things, we can apply a VDC, and there will be a sample tip potential difference, right? At this setup, we will say the electric field force between tip and the sample has 3 terms. And the second term is the one we care about, is the dc over dz times vdc plus cpd times vac sine omega t. Right? That's the second term we want to detect here. So under this force, the probe should have a deflection. So the deflection should be electric field force divided by spring constant of the probe. So it should be K or 1 dc dz VDC plus CPD, VAC sine omega t. So if we consider the PFM, it's the same setup. We apply VTB or VSB sine omega t on the probe or on the sample, and we want to get the deflection equals to D33 times VTB VSB sine omega t. So in this setup, we definitely will have this electric field force. So if we consider both of them, the total deflection should be D33 times VTB VSB sine omega t plus the, I'm sorry, I will put this, I will put these terms in the back, okay? VTB VSB sine omega t. Okay, I put this term in the back. D33 times dc over dz times vdc plus cpd. Right? That's the real thing we get in the PFM. That's the real thing we get in the PFM. Our purpose or our goal here is we only want this one. So this one will be our enemy, right? Because once we apply this modulation, the AC field, this thing will be here. How can we cancel this thing? Completely cancel this thing if we can make this 0, right? That's the idea of yesterday's KPFM topic. We apply a DC bias to cancel the CPD. After that, this term will be 0. But when we do PFM, we don't have time, or we don't have a setup to do KPFM as together, right? We don't want to get this amplitude out and to do something to get this 0. So maybe in the future, you can invent this kind of a new KPFM combined PFM. Maybe you can do this. So if I want to design an algorithm for this one, I will do this way. I will adjust VDC to make the amplitude to reach the minimum. Right? The KPFM is easy. The KPFM is adjust the VDC once the amplitude is 0. But today I'm doing the PFM, I cannot make it 0 because there will be a D33 term here, D33 term here. So if in currently we don't have this, okay? In future, if someone maybe here invent this way, yes, that's the algorithm here. That's the algorithm. Okay, but no, today we don't have it. So some researchers, they just play around with trying. So they type in different VDCs to say, if I can get the smaller amplitude, but it's not a cancellation way because your sample is heterogeneous. At each point, the potential will be different. This CPD, the potential will be different. So you have to cancel this term in real time, not just change randomly. So we need some way. So if we cannot cancel this term, if we cannot make this term 0, then we try our best to reduce this term. How we reduce this term? We cannot change the VTBSB. We are very hard for us to adjust the DC over DC. So the way we make this K large. So the larger the K, this term will be small. And then this term will be significant. So another demand for PFM is we want large K for the AFM probes. So with large K, it's a way to reduce the effect of the electrostatic charges. So that's the way. Okay. So I have to mention a setup sorry, not all times, but it's really a quite classic way, is they call it top electrode. So if this is my ferroelectric materials, and here is my AFM probes, and once I apply once I apply VSB sine omega t, there will be this term. There will be this term. If I can cancel this potential, then it's gone. So in old days, it's around 2000 years. Some researchers came up with very good idea, is they add a top layer on top of your ferroelectric materials. This top layer, they call it the top electrode. Usually it's gold, and it's around 10 nanometers. It's quite thin. 10 nanometers. So with that, we don't even need to use conductive probes. And with this kind of setup, you can consider, you already said it yesterday, right? The surface potential on gold or on platinum is quite low because it's due to the contact potential difference. There's no charge here. There's no charge here. So this term, once we add the top electrode, we add a conductive layer inside the ferroelectric, the electrostatic charge is gone. The charge is gone because no matter how you apply voltage on the gold, it's shielded, right? So that's a way to completely reduce the effect of electrostatic charges. But nowadays, I have to admit, this method is not useful for our researchers, especially our researchers are doing 2D materials. Because 2D materials is 1 or 2 nanometers. You cannot coat it with a thick gold, right? So that's just a way for old-time researchers, they are still studying crystals on it, so they can still use the this kind of layers, right? So some of you ask me in the morning if they have the top layers is okay. Yes, if we have top layers, we can still do it, but it will cover the surface, so it will reduce the resolution, and we are really looking at the gold surface, so we don't get the morphology. So that's the disadvantage of the of this top layer coating. But it's a way to cancel the. It's a way to eliminate the effect of electrostatic charges. Okay. If not, we choose large K. We choose large K. So the probe selections, the best probe selections here is we use the short cantilever. We use the large K of the probes. And the Bruker has a probe called DDESP. That's I marked red here. That's the best choice in Brooks probe selections. But this probe has disadvantages. It is expensive, and the radius of this probe is relatively large. I bring the probe today, and you can play around in the hands-on session. This probe, the radius is large. Is maybe around 50 or 60 nanometers. So it's quite a rough probes. There is another company in Ireland, and the name is Adama. They make quite good probes, and they also they just made the diamond probes, and the Dale diamond probes, they just use a way, I don't remember, it's plasma or something. So they just etch their probes, and the Adama probes, they are just doing the diamond probes, and the Dale diamond probes, the tip radius is nearly 2 to 8 nanometers, and they can even make super sharp probes to 1 nanometers or 2 nanometers. So those Adama probes, they are ideal for our PFM's the experiment setups. So if your goal is to get high resolution and try to reduce the electrostatic charges, you can consider their probes, and the price is almost the same as the price is about same as this one. So it's not expensive as our DDESP. It's cheaper, but it's better. So I used the Adama probe yesterday for the KPFMs, and it has shorter probes for PFMs. You can also consider. Okay, but this afternoon I am from Bruker, so I will take the Bruker probes. Okay. So that's the probes. So the idea is the conductive and the short and the large K. And of course, if you are old-fashioned, you have the top electrode, you have the top coating. The probe does not need to be conductive, does not need to be large K. You can just choose your sharp morphology probes for this kind of setup. Okay. So the next question we need to talk about is the frequency. So in KPI, sorry, should be not this one. Omega. So in KPFM, yesterday we said we want to detect the amplitude of our probes. And in KPFM, the probe does not touch the surface. So we want our amplitude to be large enough. So we choose what? We choose the resonance frequency. But today we are talking about PFM. The probe is touching the surface. So the probe is not free. It cannot do this kind of vibration. So we are not using the omega 0 for it. We are not using the resonance frequency for it. We just randomly pick a resonance. That's good enough. But in our instruments, some of you may play around with the hi-fi, you know, the so-called frequency response curves. Our AFM, the instrument also has the frequency response curves. They do not respond or they do not perform equally same at each frequencies. So the goal here is we want to find a frequency. At this frequency, it has the lowest noise. That's it. So in the AFM, in our AFM, especially in your dimension icon, we have studied the frequency response very well, and we found the frequency choice here. So for myself, I prefer this one, which is 19 kilohertz. And some of my colleagues say Dr. Wan Xin, he prefer this one. It's about 47. It's also okay. It's just some weird numbers. So if you're using the icon in MCPF, you can use this too, 19 or 14.7. And I know some of you are from the Chinese University or the Polytech. You may are using the dimension icon with the nanoscope 6 controllers. And in nanoscope 6 controllers, the frequency response is different from this one. In nanoscope 6 systems, the frequency below 20, they are both okay. So just depends on your instruments. Of course, if you are using other brands AFMs, just contact your technical support to ask them to tell you the frequency response. And we need to find the frequency with the low noise. Okay, so the PFM does not demand any preference on the frequencies. We choose the frequencies just due to the response of our instrument. Okay, so the next thing is about something about the instrument itself. In the afternoon, we will show you two types of the PFM working modes, or what we call it working, workspace. The one we call it optimized vertical. That means it's specially designed to detect the D33, to detect the Z directions. So it's optimized to detect the vertical. So it gives two types of frequency range. One is the so-called low speed. The frequency is from 0 to 50 kilohertz. And another type is the high speed. This one can go from 0 to 5,000 kilohertz. So you can use either of them, it's okay. If you are just for the to want to use the frequency, I choose the 19 or 7 or 47. You can choose the low speed. You can choose the low speed here, and that's the difference. And in this setup, we will have a function to to amplify the vertical signals. And inside this workspace, we can amplify the vertical signals by 16 times. So that's the 16 times gain. By default, it is enabled. So once it's enabled, your signal is magnified by 16. So if some of you want to do quantitative study to get the D33, Please remember, you times the signal by 16, reduce it back. Okay, so that's the workspace. So usually we will get something like this. So today we will have a standard sample. This standard sample is period polarized lithium nitrate. It's this one. It's this one. So onside these materials, we already polarized the sample with some stripes. And so these two stripes, they have the different polarization directions. And so we're supposed to say the phase on these two stripes, they are completely opposite. One is 0, one is 180. And on morphology, we should say nothing. And of course, the amplitude should be completely same on both stripes. But usually we will get something like this. We get the results like this because we have the electrostatic charges. We have the electrostatic charges. Why? Because we're facing up and facing down. The polarization is the same, but facing up and facing down, we expose positive charge or negative charge differently. And you know, in our atmospheres, in our airs, they are not the same. Positive charge and the negative charge, they don't completely suck the dust. So that's why these two domains, the polarization is the same, but the surface potential is not the same. So we will say the amplitude difference. So once we say this kind of structures, we would know we do not cancel the surface potential. And we will show you using different probes to do the same structures. And when we use hard probes, the amplitude is almost the same. But if we use soft probes, you will see a significant difference in the amplitude. Okay, so that's the result. And another thing is about the phase. And I don't like our way to do the phase. It makes things quite difficult to understand. So this page is from our manual, and most of you have read the manual many times about this page. And always some researchers ask me, oh, what I'm doing on this step. It's really confusing. So let's talking about our phase. The phase inside our controllers or inside our AFMs, we still try to measure it. And once we measure it, we will define a range. What's the range of phase we can detect? And in today's instrument, not just the Bruker's AFM, any other phase-related instruments, they will have a define. And the most commonly used define is from negative pi to pi, or negative 180 to positive 180. So as we said, in the PFM, in the ferroelectric materials, we only have two phases. One is 0, another one is pi, or 180. So if we want to measure the phase of these materials, we will get our phase signals something like this. So we will get 0 and 180. So our 0 is like this. Of course, we know all the measurement, there should be some noise. So the 0 will be like this. Okay, And the 180 is the same. It should be something like this. But this measurement, they should have some noise. But when we're talking about the noise, the probe comes back. If let's consider our noise is 0.1 degree. Okay, so the 180 should be 180 plus minus 0.1 degree. Okay, so 179.9 degree is good, but 100.1 degree does not exist in this instrument, right? So what we'll do, it will change due to the property of phase, because phase means 0 equals to 0 plus 2 pi. So 180.1 does not exist. It will change to what? To negative 179.9 degree. So this signal, we imagine the signal to be something like this, but the real signal will be, right? Right? The real signal should be something like this. So if we have one domain, it's 0 degree, means the polarization is follow the same direction of the electric field. And 180 degree means the direction of the polarization is opposite to the electric field. But we don't get stable 180. We get a signal jumping from 180 to negative 180. So it makes our signal or our phase images quite noisy. We don't like this kind of signals. So how to do it? So it's a way to, if we can shift our phase to another directions, then that's good. So we can either shift every signals down. So if we shift all our signals down, say 90 degrees, we will get, here is the negative 90, positive 90. We will get the, so I would say, reduced by 90 degrees. So the signals at 0 will be something like this. And the signal at 180 should be something like this. Right? Then it's kind of stable. Of course, you can plus 90 degrees. And then the results will be, this one is positive 90. And this one is 180, right? So it will plus 90 degrees goes to 270, which is negative 90. So both of them is good. So both of them is good. But so in today's facility, or I'm sorry, in today's community, they kind of forget what's the real meaning of the phase. They only remember the phase of the PFM should be positive negative 90. But no, the real definition of the phase should be always 0 and 180. Means 1. I'm sorry. Means positive 1 and negative 1. Right? That's the definition. That's the meaning why we use this phase. We shift the phase. We kind of mingle the concept, but please remember all the phase should be 1 and negative 1, 0 and 180. We just shift the phase due to the instrument demand, not the physics. It's just instrument stuff. So we reduce it or we plus it. So we can get both of them. They are okay for us. So the broker, they are good at messing things up. So they give this way to let you to show you how to optimize the phase. What they are doing is they don't explain in this way. They just told you what we are get. We are get tangent phase, right? Tangent phase equals to infinity, means our phase is at 90 degrees. Okay, so they want to get the tangent phase. So it should give you an x and y. And then this graph tells you to make one terms to be 0, which is the x terms to be 0. Once this x terms is 0, means the tangent phi is infinity. So this one will be 90 degrees. Of course, you can choose this one. And once you choose this one, your tangent phi is kind of negative infinity. Then I'm sorry, you know what my point. There's no negative infinity, but this one means negative half pi. Okay, so this one is pi. This one is half pi. Represents my plus 90 or minus 90. Okay, doesn't matter. Doesn't matter. Anyone could work. So in this in our manuals, they will told you can choose this one. You can choose this one. Doesn't matter. But do not choose this one, because when you choose this one, that means the y term, this term, the y term is 0. The tangent 0 is what? It's 0 and 180. So we don't do that, right? But I hate this stuff. It's just messed up many things, and it takes long time to understand what I am doing. So we don't need to do it. In our parameters, there is a parameter called the drive phase. This drive phase. This drive phase is just this one. You can plus or minus some degrees to get your graphs to stable at positive and negative 90. Okay, and if you understand this, if you understand the purpose of this, we don't need to confine ourselves to be positive negative 90 degrees. You can even use negative 30 and 150, right? It's the same. If you shift the phase, you lose the point of 1 and the negative 1. So any phase can work. We don't need to be 90 and negative 90, right? But it's just today's community. Some reviewers, they don't remember the theory of PFM. They just demand, oh, your phase has to be positive and negative 90. No. Okay, so any phase is okay if the difference is 180, then it's correct. And if you insist, if you want your things to be physically correct, you can get the phase signals and then get back to 0 and 180. Okay, so that's my way to understand this so-called phase. So in your future works, you don't need to open this one. You don't need to open this one. You can just directly change the phase here. Change the phase here. Okay. So yeah, that's the point of this graphs. You just adjust the phase. You can adjust the contrast on your phase signals. Doesn't matter, because we only need it to be 180 degree difference. Okay, yeah, that's the same thing they want to explain here. That's his point. This is stable at 0. This is noisy 180, and then they shift to 90 and negative 90. Okay, Next, about, okay, if I want to calculate my D33, if I want to calculate my, oh, sorry. Okay, so my theory is the vertical or the deflection equals to D33 plus dc over dj vdc plus cpd times vac vtb or sb sine omega t. Right? That's our that's the basic of our of our PFM. If we want to get this D33, I prefer to do it in this way. There is a ramp, and we want to get a graph of the amplitude of the vertical against VTB, VSB, which is the so-called in our parameters drive amplitude. And based on my theory, I increase this drive amplitude. The vertical deflection should be proportionally increased. So I will get some term, I will get a graph, something like this. And then I get the slope of this curve. The slope should be D33 plus, I'm sorry, there should be a K, 1 over K. DC, DJ, VDC, right? So if this one is cancelled, then the slope will be D33. But of course, in the real experiment, it's harder to cancel this one. So if you really insist to get the D33, we do this kind of curve. Okay, it can be done in our experiment. So the next thing we want to discuss, so we have discussed we have discussed almost every parameters, but we forget one thing. It's about this one, the drive amplitude. The drive amplitude is just this term, the VTB, VSB. We just apply a electric field. We want to detect the so-called, detect the piezo effect. But we are studying the ferroelectric materials. Inside the ferroelectric materials, it has a property called coercivity. So when we do it, we don't want our electric field to exceed the coercivity, right? So the electric field to detect the piezoelectricity should be smaller than coercivity. We don't want this field to switch in the direction of the polarization. If we do that, we are actually polarize the sample. We are actually switching, we are actually damage the domains. So we don't want to exceed the coercivity. So that means the VTB, VSB, the VTB, VSB divided by the thickness of the sample should smaller than coercivity. If you bring these terms here, this one will be a voltage, and usually this voltage, we call it switching voltage. So basically, we want this VTB, VSB, T-bias or sum bias drive amplitude to be large enough, because the larger this drive amplitude, the deflection signal will be stronger. We will get beautiful, we will get better resolution. We will get better images, but we don't want it to exceed the switching voltage. So if your sample is thick, it's okay. Go ahead, just increase the drive amplitude. But if your sample is quite thin, then the coercivity is fixed. The thickness is small, the switching voltage will be small. So if your sample is quite thin, be careful about your drive amplitude. It may exceed the switching voltage. So here is the switching spectrum, or the so-called butterfly loops. We want to get this done in the ferroelectrics. So in our AFMs, we would also try to do something. We would also try to get this kind of loops, but in the old days, they are just measuring the polarization of the y-axis. So today in the PFM, we will just using the amplitude and the phase. So let's draw it again to say how it should look like. Okay, so let me remove this one too. So we use the same story we have in the morning. We would have the PZT. We would have two types, facing up and facing down. Okay, so and we have graphs. Today, I am not doing the ferroelectricity analysis. What I am doing today is the PFM. So I have the amplitude and the phase. And I am not applying a electric field. What I am applying is a DC voltage. So I want to apply a DC. I want to apply a DC electric field. Since this one already occupied one, for example, if I apply the AC electric field or the AC voltage on the sample bias, I can apply tip bias to be a DC voltage, or I can do it opposite way. I apply the AC current, AC voltage on tip, and then I can adjust the DC voltage on sample. Okay, that's the experiment setup. So usually we apply the AC bias on the sample, and then the tip bias will be freed for us to apply DC voltages. So I use the example on this slide. So the x-axis will be weight tip. Okay, if you divide it by the thickness of the sample, it will be the electric field. So I come from beginning. So the PZT. So again, the time 0, the total P is 0. So my starting point is here. The total P is 0. I'm sorry again. This blue means increase, and the red means decrease. Okay. So I starting from 0. At the 0 time point, the polarization is 0. The polarization is 0. So my amplitude, once I increase the VTB, the polarization, I would change the direction of facing down to facing up. So the amplitude should increase. Once it reaches the maximum, everything is polarized. So at this point, it's 100% up. So my amplitude should be slowly slowly increased, right? And then I reduce the voltage. It follow this line, goes to here. This point is the intrinsic polarization. And then I goes down to reach the coercivity. And this coercivity, we call this one switching voltage. Okay, and then after this point, I start to change the direction of facing up to facing down. So my polarization should reduce, but I am detecting the amplitude. The amplitude should always be 0. So the amplitude is actually the absolute value of D33, or the absolute value of polarization. So my voltage, so my polarization should goes down, but my amplitude cannot go down. So it should, so if we consider this line, it should be something like this, but it's absolute value. So it's up, right? Until it reach 100% facing down. And then the increase will be slowly. And then at this point, I will increase my voltage again. So once I increase the voltage, I should follow this line to go through these points. And if you take a look at here, there should be something like here, right? I'm sorry. Reach these points. But since it's absolute value, it should facing up. And then I continuously increase. Once I continuously increase the voltage, the facing down is facing up. So the total polarization is increased, but the polarization absolute value is reduced until it reach another coercivity. On this axis is voltage, so it's another switching voltage. And then it finally goes up, so it should go up. So that's the loop, how it should looks like. So usually we would draw it in this way. The blue curves is increased, the red curves is reduced. It is decreased. So the positive switching voltage should be on blue curves. The negative switching voltage should be on red curves. So that's the means of the counterclockwise. Okay, so if you are continuously back and forth, forth and back the voltage, so we can ignore this curve. So the finally we get is something like this. We will call it butterfly loop. Okay, that's the piezo response. It's famous butterfly loops, and this one is much more beautiful than this one. Okay, it's hopefully we can get a beautiful result this afternoon. Yeah, but at least its direction is correct, and some of researchers get the wrong directions. They get the blue branch here and the red branch there. Then it's wrong. Then this one should always be counterclockwise. Okay, then let's talking about the phase. So the phase is the same thing. At the time 0, The phase should be, I don't know, it's 0 or 180 because there is no polarization. There's no polarization means there is no vibration. There's no vibration. The phase usually is kind of random thing. So I don't care about the first points. The phase is random thing. But once I gave a positive voltage on it, I will make the facing up to be dominant. Once the facing up is dominant, the phase should be 0. Okay? So I keep going until I reach the maximum. And then at this point, I am going to reducing. So I keep going until at this point. This point is the switching voltage or is the coercivity. After this point, the facing down will be dominant. If the facing down is dominant, the total polarization will be negative. Once it's negative, once it's negative, the phase will be 180. So at this point, the phase will jump to 180 and then then it will be completely 180. Okay, 100% polarization. Okay, after that, I increase my voltage. And in the negative voltage, it should be always facing down dominated. And then I keep going. Once I reach the positive coercivity, the facing will be something 0 or random phase. And I increase the voltage a little bit. The facing up will be dominant. The polarization will be positive, and then the phase will be 0. So I should get something like this. Oh, this one is okay. So this one is okay. So the phase signals is relatively simple. So it's kind of a square. It's kind of square, but the amplitude is kind of butterfly. So from the phase we can get this is the switching voltage, and this one is another switching voltage. Okay, but as we said, we don't use this kind of setup because we would like to shift the phase. So if we shift the phase lower, then we will get some loops like if we shift the phase lower, we get the 0 degree to be negative 90, 180 to be positive 90. So we will get the curve to be right, something like this. This one is the 90, this one is negative 90. Okay, if we plus 90 degree, we shift the phase up. We shift the phase up, we will get something like, don't have the pen. We shift it up. So this term will be the 90. So this one is 90. This one is negative 90. So this branch will be 90. And this branch will be negative 90. So okay, right? We will get something like this. But no matter how you switch, be careful. The positive switching voltage is on blue. The negative switching voltage is on red, no matter how you switch it, because that's the property of the counterclockwise of the ferroelectric hysteresis loops. So only this two is correct. So all the others, for example, you can say something like this. This one is wrong, right? This one is wrong. It's actually clockwise. This one is wrong. Only this two is acceptable, and this one. So the direction is important, and we have a joke that in the old days, the researchers will print the paper out to read it, and then there's no color, so under the black, all these things they look the same, so they just ignore it. So no, nowadays no, we want it to be accurate. Okay, sometimes in your experiment you can get the loop something like this. So actually, the reason why you can get some loop like this is because you still have the surface potential. And the surface potential can be changed by your tip valves because you are actually inject the ions or inject the electrons. So if you find something like this, the direction is wrong, it just means we still have the potential. Okay, so once we are really doing the ferroelectric, it's only like this. Okay, we're almost there. So we have another workspace. We will also show you another workspace is called V-H, means vertical and horizontal captured together. So we will open two sets of channels. The amplitude 1 and the phase 1 will be the vertical channels. Amplitude 2 and phase 2 will be horizontal channels. And the vertical channels tells us D33 or out of plane. And the amplitude 2 and the phase 2 tells us the horizontal signals, the D34 or D35, which is in plane components. Okay, so let's spend the last 10 minutes about the contact resonance. It's a long story, but let's go through it a little bit. Okay, the contact resonance, as we said, we don't have the frequency dependence in the PFM because the probe touch on the surface. The probe touch on the surface. So there is no way for the probe to free vibrate. But in the world of vibration, there's not only one way to do the vibration. You know the bridge. The both sides of the bridge is fixed, but the bridge can still vibrate, right? Like yesterday's Napoleon story. Anything can be vibrate. It does not need to be a free cantilever. So the way to describe vibration, we use the beam theory. And the beam theory has been established by this guy, Euler or something. It's a mathematics. It's that's the name. Yes, Euler. And another guy is the Sam Bernoulli. There are many famous Bernoullis. It's a large families, and some guys developed the fluidics. Some guys want to find the fastest dropping curves. Those guys, they play around with math, And also we have this French guy. I forgot how to pronounce it in French. In Chinese is Lagrange. So those guys, they established the beam series. So this beam series, they just want to tell, I have a beam. I have a beam. This beam can be fixed on one side or can be fixed on both sides, no matter how. Then on these beams, I can apply a force on the beam. And then this beam itself should have the elastic force. So same as yesterday's story. Yesterday's story is we consider the whole beam as a point. So for this point, the F equals to Kz plus Fts. And the F equals to the Mz second order derivatives. And today, we don't do this so roughly to consider it a point. We consider it as a beam. And then on each part or onside this beams, they would follow a similar beam theory. And you can tell this part, that's the Newton's law. That's the second Newton's law. That's the acceleration at this term. And this part is I apply a force. And this part, you see a E, you see a modulus here. So this part is the Kz, that's the Hooke's law. So we don't talk about that. So after we solve this kind of equation, this equation is more complex than yesterday. After we solve this equation, we will get this kind of thing. This thing, we call it vibration. And this vibration, if we are from yesterday's study, the vibration, the frequency of the vibration is fixed. But today, we are talking about a beam. And onside the beam, we do not get a fixed frequency, but we get a set of frequencies. And these frequencies, they have different orders. And the different orders means it has different vibration modes. For example, this n equals to 1, and on this beam, one side is fixed, one side is free. That's our AFM cantilever. So n equals to 1 means the probe can be moved like this, which is the vibration we described yesterday. And its frequency, the resonance frequency, we get out yesterday, K/M. And then this cantilever can move in another ways. For example, it can move like this. So onside the cantilevers, not every point they are moving in the same fashion. That's the second order, third order, or in another word, it's the second order harmonic oscillation, third order harmonic oscillations. And today we can show you how this kind of vibration looks like in the AFM. We can say this kind of higher order vibration. Okay, not interested. We don't talking about this. We are talking about this. So our probe is one side fixed, and another probe, another side of our probe is touching the surface. We are doing the PFM. Sorry. The probe, one side is fixed, another side is touching the surface. And so how strong it touches is controlled by me, because I can apply set point to control how the probe is touching the surface. So this part is decided by me. So in this kind of setup, I know the probe can also move. It can move in this way. That's the first order. It can also move in this way. That's the third order. Of course, there is a second order. There is a second order. So After that, I can understand the probe is still have some resonance vibration. And this kind of resonance vibration, we call it contact resonance. Contact resonance. So if our frequency is just at the contact resonance, then the vibration or the deflection is magnified by Q times. And so if our signal is quite weak and we wanted to amplify our signals, we can choose this frequency to be contact resonance frequency. And usually the contact resonance frequency is about 3 to 4 times omega 0. So if you found your sample is so weak, the piezoelectricity is so weak, you can consider to use the contact resonance frequencies, and we will show you how to find it. So that's one screenshot of how to find the contact resonance frequencies. And this is the this graph we are using the SCMPIT. The frequency is about 75 kilohertz. So its contact resonance is less than 400. So we find this peak. So that's the contact resonance frequencies. So if your signal is weak, you can use it. But the headache of the contact resonance is highly dependent on how hard the probe touch the surface. So the mechanical property of your sample changed. The contact resonance frequency can change. It's not a fixed value. So it's better to scan to find the contact resonance on each point. And we will, let me see if we have that function in the software. But if we have, or if you need, maybe you can consider to use that in the future. Okay, so that's the results. So if we are using the contact resonance, the amplitude is quite large. Okay, so that's the way I have mentioned. We have a way to find the contact resonance on our samples at each point, and then we can get the amplitude and the phase on the contact resonance frequencies on each point. That's the so-called data cube functions. And if we have, or if your AFM has these functions, you can give it a try. And that's the results. And we also had the we also use the same theory about the lateral PFM, about this directions in plane components. And the in plane components, we use not the contact resonance, we use this torsional resonance. And this torsional resonance, if you want to try, the torsional resonance is about 10 times. It's about the 10 times of the it's about the 10 times of the omega 0. Of the omega 0, and this is the results I get in Fudan University. Use the torsional resonance to amplify it. Okay, and that's not useful. That's not useful. So yes, if you have external AC if you want to use your own amplitude source, you have some very good power source, you want to use that, you can also net our instrument to output the AC signals and use your machines to apply AC bias on the sample. And if we have this kind of thing, or have other high voltage power source, and you can apply high voltage DC signals on the samples, because sometimes the switching voltage is small, and then our T-bias is good enough. If your sample is sick, the switching voltage equals to the coercivity times the thickness. If your sample is too thick, then the switching voltage will be large, and then you may need to use the high voltage thing to get the hysteresis loops. Okay. Okay, that's all about the PFM. It's a long story. So in the hands-on session, we will take a PZT to show you the get PFM results, get hysteresis loops. Hope we can get it today. And I know some of you had to bring your own samples. We can also give it a try. And I will show you how to optimize the phase. And there's also a parameter called bandwidth, those stuffs. And we hope to show you how to get a nice PFM results. And the loops and the D33, those stuffs, we will also get it done in the hands-on sessions. Okay, so that's the whole story of the piezo response, the PFMs. We'll also have more advanced series, such as the contact resistance or something. And even in today's setups, you are playing around with the 2D materials, and these 2D materials has quite a unique symmetry, and we can even get quite a unique this ferroelectricities, and hope we can get it better and better, and the PFM would advance with yourself. Okay, thank you so much. Thank you.